All right, so let's pick up where we left off yesterday. Yesterday, we did talk about um, equilibrium constants and looking at what side of the reaction is favored based off of that number. And we did talk about at the very end that this is a constant. So even if we change the amounts of our reactants that we start with, they will end up at the same ratio at equilibrium, having the same equilibrium constant. So that will not change throughout the course of the reaction. Now, what if we don't know that we are at equilibrium? In that case, we're going to use a reaction quotient, which we're going to represent as a capital Q. So this is going to be the exact same expression, the same formula as the equilibrium constant. So we're still going to have the products over reactants. However, we're using the concentrations that may not be at equilibrium. So we might be using our initial concentrations or concentrations after a certain amount of time. So the reaction quotient is a numerical value that shows where the system currently sits compared to the equilibrium position. So it might be that we have not reached equilibrium yet, and it will tell us which way the reaction needs to go. Does it need to make more products or more reactants to reach equilibrium? So the reaction quotient, like we said, is going to be the same expression, the same formula, the products over reactants, but it does not have to use the equilibrium values. So here's an example where we can do reaction quotient. So here we have hydrogen iodide producing that hydrogen iodide gas. It tells us that the K for this equation, so using equilibrium values, K is going to be 60 at 350 degrees Celsius. A lot of times you will see temperatures there because temperature is the only thing that's really going to affect that K value. And it tells us that our concentrations for hydrogen iodide are, or iodine, excuse me, are 0.01 molar, and our hydrogen iodide is going to be 0.05 molar. So it did not tell us if this was at equilibrium. So we would be finding Q for this. So we can write out our expression. So we do have Q is equal to the product, which is the hydrogen iodide, which because there's a coefficient of 2, that will be squared, over our hydrogen times our iodine. So using that expression, we can plug in the values that we were given. So the hydrogen iodide is 0.050. Don't forget to bring down your exponent. The hydrogen iodine are 0.010 and 0.010. Remember when you're typing this in, because you have multiple numbers on the bottom, make sure that they are both divided by. So that is going to allow us to solve for Q, which when we punch in 0.050 squared divided by the 0.010 times 0.010, I got that Q is equal to 25. Notice that Q does not equal K. So we're going to look at what does that mean? What does that information tell us? So let's look at comparing Q and K. So this is where we figure out what does that value actually tell us. So if Q is equal to K, so we find Q and it is the same as K, that means that we are currently at equilibrium. Now, what happens if they don't match? So if Q is less than K, that means that the reaction is going to proceed towards the product. So we need to make more products to reach equilibrium. And if Q is greater than K, that means the reaction is going to proceed towards the reactants, meaning we need to make more reactants to reach equilibrium. Now, how I like to remember this, sorry, I lost my mouse. If you put these in alphabetical order, so flip it around, and we say that K is greater than Q, when they're in alphabetical order, that greater than or less than sign acts as an arrow. So that's going to tell us that the reaction is going towards the products. If we have K is less than Q, yet again, when they're in alphabetical order, that acts as my arrowhead. So the reaction needs to proceed toward the reactants. All right, so here's just a graph kind of showing that for the K in this example is that 1.45. That's the red line that goes horizontally. Q is represented by the blue line. So when Q and K are equal, that's when the two intersect. That means that we are at equilibrium. Notice if we are on the lower end, where K is going to be greater than Q. I'm flipping it so you can look. That means we need to go towards the products and make more products in order to reach that equilibrium line. If we're on that upward slope at the top, where K is less than Q, we need more reactants to reach equilibrium. And you can even see, kind of looking at the particulate level, where if we're at equilibrium, you know, the number of particles in general, there are going to be slightly more products because it's greater than one. But notice that if we're further to the left, there's only reactants. So we would need more products to reach equilibrium. The further to the right we are on the graph, there's more products. There's more of those red dots. So we would need to revert back into reactants to reach equilibrium. So let's look at this one. Here it gives us the reaction of PCl3 gas and chlorine gas producing PCl5 gas. It says at a given temperature, the following equilibrium concentrations are observed. So this is saying we are at equilibrium. It wants us to determine the value of the equilibrium constant at this temperature. So since we're at equilibrium, we are solving for KEQ. So we have our product on top, which is the PCl5, divided by our reactants on the bottom, the PCl3 times the Cl2. So if we plug in the values that it gives us, PCl5 is 0.00670 molar. On the bottom, PCl3 is 0.00300. Cl2 is 0.00200. There are no exponents because there were no coefficients. So this gives us a K value. If we do the 0.0067 divided by both, the 0.003.00 and the 0.00200, we get that our K value is equal to 1116.6. For sig fig's sake, everything had 3 sig figs. So I'm going to change that to 1120 to keep it at those 3 sig figs. So that is our K value at equilibrium. All right, so then looking here, it says at the same temperature, some of the chlorine, the phosphorus trichloride and phosphorus pentachloride are mixed at the following concentrations. So it's not telling us that it is at equilibrium. So we don't know if it's at equilibrium or if it needs to shift one direction or the other. So here it says in which direction will the reaction proceed to achieve equilibrium. So since it didn't tell us it was at equilibrium, here we are going to be solving for Q. And remember, it is the exact same formula that we had on the previous slides. The PCl5 was on top. That's the 0.0038. The PCl3 was on the bottom, the 0.063. And the Cl2 is on the bottom. That's the 0.0050. So when we put that in the calculator, so 0.0038 divided by both the 0.063 and the 0.0050, we get that our Q value here and everything here had two sig figs, so our Q value is going to be 12. It's like 12.06 on the calculator. So notice that this is not the same as our K value. So we are not at equilibrium. And to compare these, we need to compare K to Q. So remember, if you put these in alphabetical order, it gives you that arrowhead to show which direction to shift in. So we say K was 1,120, Q is 12. K is greater than Q, meaning that the reaction shifts towards the right. So reaction proceeds towards products. So we're going to have to make more products in order for this to reach equilibrium.